The topic of this video is dimensional analysis, or the factor label method. This is a method that will allow us to convert between units in our moles and stoichiometry unit, but it can also be used to make any unit conversion. So if you're trying to convert between inches to meters or miles to kilometers and so on. So dimensional analysis is going to involve the simple formula. My unknown is equal to my given times want over have. So in reality, this isn't the actual dimensional analysis formula, but this is our format that is going to help us make sure that we can line up whatever we want to convert the units from, all right? So whatever our given is to whatever unit we desire. So the units of our given and our have are always going to be the same because if I divide, let's say I have grams, I have to cross out grams and I want moles, right? If I have G and I divide by G, they'll end up canceling. So the units of my given and my have will always be the same. The want is the unit that I want to end up with. All right, so this, again, this general format is going to help us make sure that we're canceling the units that we want and we're ending up with the new unit that we want to obtain. So here's an example. How many seconds are in one AP chemistry block? So what do I know? Well, I know that I'm in chemistry. This will be my given. So I'm going to say G equals. I know I'm in chemistry for 80 minutes. And my want, I want to figure out how many seconds that's equal to. So my general, again, format is given. So what am I given? Well, I'm given that I have 80 minutes of chemistry. I'm going to multiply that by inequality. The want unit, what I want to end up with, is going to go on top. So I want to end up in seconds. The have is what I have to cross out. Well, I have to cross out minutes. Dimensional analysis really is making sure that whatever units you're trying to cancel are kind of kitty corner to one another. And if I were to have to make various steps to get to my desired unit, I could just stack up these equalities. I don't have to in this case, but I do need to know the relationship between minutes and seconds. So I know 1 minute is equal to 60 seconds. So I'm going to put that equality into my parentheses here. 1 minute is 60 seconds. And now it's simple math. Now the beauty of dimensional analysis is I can see the canceling of my units, and then anything on the top I'm going to multiply by, and anything on the bottom I'm going to divide by. So I'm going to end up getting 80 times 60 and then divided by 1. Well, that's going to give me 4,800 seconds. So again, this is just going to give us a general format to get to a desired unit. Now, we're going to do a couple of chemistry examples in a moment. In order to complete those examples, we need to know the following equality. Just like I knew 1 minute was equal to 60 seconds, I need to know the following equalities to be able to convert between moles and grams, moles and liters, and so on. So remember that the concept mole is very similar to the concept of dozen, right? So if I say I'm going to bring a dozen donuts to class tomorrow, that means I'm bringing 12 donuts. If I have a dozen cars at home, that means I have 12 cars. The word dozen signifies a specific number. The same is true about the word mole. It's just that number is a lot larger than 12. 1 mole is equal to Avogadro's number, which is 6.022 times 10 to the 23rd molecules or atoms. Now that's a lot of molecules and atoms, but think about atoms. They're super small. So 6.022 times 10 to the 23rd atoms might not really be that huge of an amount of mass of something. For example, it would only be 18 grams of water. But 1 mole is always equal to this number. And again, this is Avogadro's number and it's right in your reference tables. 1 mole is also equal to 22.4 liters of gas at STP. Now this is key. It's only for gases at STP, so only for gases at standard temperature and pressure. 1 mole is also equal to the gram formula mass. So this is often the most difficult thing to kind of grasp. It's not always equal to a set mass, all right? So think of that word dozen again. If I had 12 pencils, it's by no means going to weigh the same as 12 cars. Same thing here. If I have 1 mole of, let's say, oxygen atoms, I have 6.022 times 10 to the 23rd. Well, oxygen has a mass of 16, right? Um, However, if I have 1 mole of, let's say, helium, well, we'll do hydrogen atoms. I have 6.022 times 10 to the 23rd of those. But hydrogen is going to have a significantly lower mass, right? It's just going to be 1 AMU. Both of those are diatomic, so I technically have to double their masses, but you get the point. Oxygen does not weigh the same as hydrogen, just like pencils don't weigh the same as cars. So 1 mole is equal to that gram formula mass of our atom or our molecule, all right, whatever we're dealing with. So make sure this is in your notes. This is really, really important. The other thing that I would strongly encourage you to put into your notes is this mole map. This is going to be key as we're mapping out the process of converting our units. So the way this works is moles are in the center, right? Moles are kind of our go-to for these conversions. You can convert from moles to volume because you know 1 mole is equal to 22.4 liters of gas at STP. We can convert from moles to mass because we know 1 mole is equal to the GFM, the gram formula mass. And we can convert between moles and molecules because we know 1 mole is equal to 6.022 times 10 to the 23rd atoms or molecules. And you'll notice this same graphic organizer is repeated on the other side. They're separated by these pink dots. The difference here is this would be for sample A. So this would be maybe water in a reaction. And this is for sample B. So maybe I'm trying to go from moles of water to moles of CO2 in a chemical reaction. The only way to jump over this pink line is to do a mole to mole ratio. All right, how many moles of water were there for every moles of carbon dioxide? And I'll show you where to get that mole to mole ratio. But this is, again, going to allow us to map out the steps in our factor label method or in our dimensional analysis. All right, so let's take a look at our first example. It says, what is the mass of 2 moles of carbon? So I always like to write down my given and my want. So my given is 2.0 moles of carbon. My want is grams of carbon. Now I can use this mole map to help me figure out what to do. So I'm dealing with carbon. So I'm going to stay on one side of that pink dotted line, one side of that mole map. And I'm trying to go from moles to grams. So again, my one side is going to be carbon. And I'm trying to go from moles to grams. So I can see that's just going to take me one step, right? I'm going from moles to grams, and I only have to go through this arrow. So that is going to tell me I only need one equality when I go to set this up. So I know my given is 2.0 moles of carbon. Make sure you include units and a label, so moles of carbon. And I know I'm going to multiply that by an equality. My want, the unit I want to end up with, is going to go on the top, so that's grams of carbon. And the unit I have to cross out is going to go on the bottom, so that's moles of carbon. Remember, you always want the thing that you're crossing out kitty corner. And now I have to think about my equality. Well, I know 1 mole is equal to the following: 6.022 times 10 to the 23rd. That's atoms or molecules. Well, that's not what I'm dealing with. I want grams. It's equal to 22.4 liters. Again, that's not what I want. I want grams. Or it's equal to the GFM, the gram formula mass. Well, that's what I want. I want grams. So I'm going to put this equality. 1 mole is equal to the gram formula mass of carbon. So where do I get that gram formula mass? Well, I can look it right up on my periodic table. So it should be like 12.01. You might get another sig fig from your periodic table, but I'm going to use 12.01. So now everything on the top is multiplied, right? So everything on the top is multiplied. So 2 times 12.01 is going to give me 24.02 divided by 1. My moles of carbon are going to cancel, and I'm going to be left with grams of C. So that is going to be my answer with one exception. I have to take into account my sig figs. So remember that Atlantic Pacific method. So there is a decimal point present. I'm going to count from the Pacific Ocean in, and I'm not going to start, I'm going to start counting my first digit, and I'm not going to stop until I hit the end. So there are 2 sig figs here. And here I have 1, 2, 3, 4. This is just a counting number, right? 1 mole is not a measured quantity. This is rounded though, so I'm going to count it for sig figs. This guy is 4 sig figs. Whenever I multiply or divide, I'm going to use the lowest number of significant digits or figures. So in this case, I'm going to keep the 2 and the 4, but I'm only allowed 2 significant figures. So 24 grams of carbon is going to be my answer. All right, so my next example says, how many liters are in 25.4 grams of carbon dioxide gas at STP? So this is significant, this gas at STP, because this is letting me know I can use the equality 1 mole equals 22.4 liters. I'm going to make a list of what I'm given and what I want. My given is 24.5 grams, and my want is the number of liters. So I'm dealing with CO2 in both cases. I'm going to stay on the same side of that mole map. And this time I want to go from grams to liters. So let's take a look at this mole map. Let's erase my previous markings. So now I want to go from grams to liters, to volume. So there's no direct route here, which means I'm going to have to do 2 equalities. The first one is from grams to moles, and then the second one is from moles to volume. Again, there's no direct route. So when I do my dimensional analysis, it's going to involve 2 conversions. One from grams to moles, and then one from moles to liters. So if I go back to this example, I have 24.5 grams of CO2. Remember your units and your labels. I know my first jump is going to be to get rid of grams and to be left with moles. And I know my equality is 1 mole is equal to the gram formula mass. So for CO2, that's about 44.01. All right, so I would know my carbon, there's 1 of them with 12.01 grams. My oxygen, there's 2 of them, 16 for each of those. So I would do 32 plus 12.01 to give me 44.01. But I'm not done. That gives me moles. I want to get to liters. So I'm going to multiply this by another equality. This time I have to get rid of moles of CO2, and I want to end up with liters of CO2. If I needed 3 steps, I would add another equality here. And then I write what I know. 1 mole is equal to 22.4 liters. I can see that my units are going to cancel. Moles of CO2 are gone, and I'm left with liters of CO2. Everything on the top here is going to get multiplied. So 24.5 times 1 times 22.4. And then everything on the bottom, I'm going to divide by. So I'm going to divide by 44.01 and 1. If I plug that into my calculator, I get 12.47 liters of CO2. Now I check my significant figures. I have, counting from the Pacific Ocean, 1, 2, 3 sig figs. I'm not going to count the ones, all right? Those aren't measured quantities. I have 1, 2, 3, 4 sig figs, and I have 1, 2, 3 sig figs. So I'm going to keep 3 sig figs. 12.5 liters of CO2 is going to be my answer. All right, so at this point, I would like you to copy down the following questions in your Cornell notes, and I want you to try to answer these questions. In a minute, when you hit play again, I'm going to give you the answers, but I am not going to show my work with these. So this is a way for you to check to make sure that you're on the right track. I am going to include a second video on the website, on our class website. So if you do not get the correct answer, you can go back and you can watch that video. If you get the correct answer, don't worry about it. And I do expect these examples are included in your Cornell notes. I will be looking for them when I collect them and grade them. Okay, so for our answers, for number 1, you should have gotten 296 moles of copper nitrate. For number 2, how many atoms of nitrogen are in 2 moles of copper nitrate? You should have gotten 2.4 times 10 to the 24th atoms. This one is tricky. Nitrogen and copper nitrate are not the same. So this time you're going to have to jump over that pink dotted line. Again, if you don't understand how to do that, then after you watch this video, make sure that you go through and you look at these practice problems done out. And then number 3, how many liters are in 100 grams of CO2? Our answer for this one is going to be 50.9 liters of carbon dioxide. So check your answers. If they don't line up after this video, make sure you go back and you revisit these practice problems and take a look at my examples with the work done out. The next examples are going to involve some stoichiometry. So they're not just going to be converting from one unit to another. Now we're going to be looking at chemical reactions and going from maybe how many reactants I started with to how many grams of products I'm going to produce. The nice thing about this is it's always going to use that given times want over have as well as that mole map. All right, so everything is going to use kind of the same tools to get to my answer. So my first example says how many moles of oxygen, so that is my want, right? I want moles of oxygen are produced when, so here's my given, 10.5 moles of H2O are decomposed. So now I know that I'm trying to go from one sample to another, from O2 to H2O, and I'm trying to go from moles to moles. So if I go back to that mole map, I know, let me do some erasing here. If I go back to that mole map, I know I'm going from moles of one thing to moles of another. And specifically, we're going from moles of, let's see, H2O to O2. So I'm going to label the left side, oops, the left side H2O, and the right side, I think it was CO2. And we're going to see that this is just a one-step process. If I'm going from moles of one thing to moles of another, I'm going to use my mole to mole ratio. So there are 2 ways to get a mole to mole ratio. I could look at my formula. So this is what you did for one of the practice problems, or this is what you will notice that you do as you watch the second video. So I could say in 1 mole of water, there are 2 moles of hydrogen. So if I'm given 2 moles of H2O, and I'm trying to figure out how many moles of O, right? I can do a mole to mole ratio, go from moles of water, 1 mole of water, actually, let's say I want not moles of O, but moles of H. 1 mole of water has 2 moles of hydrogen, right? That's basically like saying, here's one person, for every one person, I have 2 arms, right? So on every one H2O, I have 2 H's. There's 2 of those hydrogens coming off of my water, just like my little person that I drew. That's one way to do a mole to mole ratio, so to use the equation. The other is to use the coefficients in my balanced chemical reaction. That's what we're going to do now. If we're given a reaction, we're going to use those coefficients. So I know it's going to be a one-step process going from moles of one thing to moles of another. So going back to my example, I have a given of 10.5 moles of H2O. Make sure you have your labels, right? Your unit with your label. I have to get rid of moles of H2O, and I want to end up with moles of O2. This is why it's important to put your labels. Otherwise, it's moles, moles, and moles, and it gets very confusing as to what's going on. So now I'm going to use my coefficients and my balanced chemical reaction. So I look out in front of my water, there's a 2. So that means I'm going to put 2 moles with my water. And then there's nothing in front of my O. So remember, we don't write ones in chemistry. So that nothing implies that there is 1 mole of O2 that's being formed. I can see that I've set this up correctly. My moles of water cancel. And now I'm just left with math. 10.5 times 1 divided by 2. So if I plug that into my calculator, I'm going to get 5.25 moles of oxygen. Now, according to my sig figs, these are counting numbers. These aren't measured quantities, right? They're coming from my chemical reaction. So I'm only using that 10.5. There's a decimal point present, and I'm going to count until I hit the last number, right? Start counting at my first digit and count all the way to the end. So I have 3 sig figs, which means I need 3 sig figs in my answer. So 5.25 is the correct response here. Our last example says how many liters of H2 will be produced when 25 grams of H2O are decomposed. So my given is 25.0 grams of water, and my want is liters of H2. So again, I'm going to cross that pink line. I'm going from one substance to another. But this time it's not from moles to moles, so it's going to involve some additional steps. So if I go back to that mole map, let me erase my previous work. If you recall from the previous slide, we were given, so my given here was 25.0 grams of water, and my want was the liters of H2. So I'm going to call this side hydrogen and this side water. I can only go from one substance to another by crossing that pink line. All right, so let's see. Let's plan out my route. I'm starting with grams of water. So this is my water side. Here's my grams. And I'm trying to get to liters of H2. So this is my H2 side, and I'm trying to get to liters, which is a volume. So how many steps is this going to involve? Well, 1, 2, 3. So I'm going to need 3 equalities total. The first step is going to involve a conversion between grams to moles. The second step is going to involve a conversion from moles of H2O to moles of H2. And this time I'm going to use the coefficients in my balanced reaction. And then my third step is going to involve the conversion between moles of H2 to liters of H2. So 3 steps total. So if I go back, again, this map is just to help plan out your process, to tell you how many steps we're going to use and so on. So if I go back to this example, I know my given is 25.0 grams of water. You know, the first thing I want to do is to go from grams of water to moles of water. So I have to get rid of my grams of water. And I want to be left with my moles of water. What's my equality? 1 mole is equal to the gram formula mass. So the gram formula mass of water is 18.016. That is not the end of my work though. So I just went from grams to moles. So if I go back to this mole map, grams to moles, my next step is to go from moles of water to moles of hydrogen. So I'm going to set up another equality. I want moles of water on the bottom, and I want to end up here. So I have to cross out moles of water. I want to end up with moles of H, right? That's the new box I'm trying to get to. How do we go from moles of one thing to moles of another? Well, I'm given a reaction, so I'm going to use these coefficients. So there's a 2 with my H2O, and there's a 2 with my H2. So my units are going to cross out my moles of H2O, but I'm not at the desired unit. So I'm going to go back to my mole map. I've just arrived at this square right here, this rectangle right here. So one final step is to go from moles of my H2 to liters of my H2. So one final equality to write. And I have to cross out moles of H2, and I want to be left with liters of H2. And then my equality is 1 mole equals 22.4 liters. You can see my moles of H2 cross out. And now I'm going to multiply everything on the top. So 25 times 1 times 2 times 22.4. And then I'm going to divide by everything on the bottom, my 18.016, my 2, and my 1. So I plug that all into my calculator, and I'm going to get 31.1 liters. Look at my sig figs. I have 3, 1, 2, 3. I have 1, 2, 3, 4, 5. These don't count. These are just numbers for my coefficients. And this one has 1, 2, 3. So 3 sig figs is what I want to round my answer to. So this concludes our video. I cannot stress enough how important this mole map is to plan out your steps, as well as these 3 equalities. If you know these 2 slides, you should be able to do any conversion, whether it's in chemistry or any other class. All right, it will always be able to get you through those conversions. And as always, we'll do a bunch of practice next class on this.